Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello all, and welcome to this session on machine learning supporting ecology. My name is Andrea Manara from the ITU, the International Telecommunication Union. It is an honor for me to introduce a new episode in the GeoAI Discovery Series. This series is curated by three outstanding geospatial professionals, Nadine Alamé, Maria Brovelli, and Barbara Ryan. We launched this series on February 1st. If you missed the previous episodes, don't worry, you can watch the recordings of those events on YouTube or on the neural network to which you are connected right now. Without further ado, let me now introduce Maria Brovelli. Maria is a professor of GIS at the Polytechnique di Milano and a member of the School of Doctoral Studies in Data Science at Roma La Sapienza. She is also a member of the ESA Advisory Committee on Earth Observation, co-chair of the United Nations Open GIS Initiative and deputy chair of the UNGGIM, the Global Geospatial Information Management Academic Network. She is also the author of over 100 scientific index publications and guest editor of 11 special issues. She will moderate this session and introduce you to the outstanding speaker of today's session. Maria, the floor is yours.
Thank you, Andrea, and very welcome to everyone to this new episode of GeoAI for Good. I hope that you attended already the other meetings, the other events, or if you didn't, as Andrea said, they are available on YouTube. But today we are here for listening to a new speech presented by a colleague of mine, a friend also, and as always, we are hosting the best researchers in the domain of machine learning related to GeoAI. So it is a very pleasure to introduce to you Professor Devis Tuia. And Devis completed his PhD at the University of Lausanne in Switzerland, where he studied kernel method for hyperspectral satellite data. Then he decided to travel the world as a postdoc. First of all, he had been to the University of Valencia, then to CU Boulder, and finally back to the EPFL. in 2014, he became assistant professor at the University of Zurich. And in 2017, he moved to Wageningen University in the Netherlands, where he was the chair of the Geoinformation Science and Remote Sensing Lab. Then, since September 2020, is back to the EPFL, where he leads the Environmental Computational Science and Earth Observation Laboratory in Sion. There, he studies the Earth from above with machine learning and computer vision. And today, his speech is about how we can use the machine learning for as an interface for understanding the conservation and biodiversity. So at the interface of the machine learning and conservation. So biodiversity and geospatial science supported by machine learning are the main topics that we will discuss today. So thank you so much, Devis, for accepting being here. I'm very excited and I want to learn something from your presentation. So Devis, please come here on the stage and yes, I will give you the floor.
Here I am. Thank you very much, Maria, for the kind introduction. Good afternoon, everybody, or good morning if you're in another time zone. And yeah, it's a big pleasure to be here and to participate to this GeoAI for Good seminar series. And the idea is to talk 45 minutes about how we can use AI to help wildlife conservation and ecology in general, but also how the loop can be closed and how ecology can help advance AI and machine learning and computer vision. So I hope you can see my screen. Maria, if you can just confirm that everything is well.
Yes, yes.
Yes, yeah. Fantastic. So yeah, I'm setting the stage with this first slide just to show you the kind of geographies, the kind of places where we will be discussing in this presentation. It will be mostly in Africa, even though the concepts apply worldwide, wherever you want to monitor populations and try to make a difference for the protection using AI methodologies. All right, so well, the starting observation that basically got me into this whole animal conservation topic back in the day, it's almost 10 years ago, was this observation that the decline in biodiversity is something that is coming very, very fast, accelerating, and that it has terrible consequences for us human beings, but most importantly for the planet and all the other species that we share the planet with. So what we have been observing is that we are losing an incredible amount of populations, and species are disappearing at a very alarming rate. Let's say that we are, I hope you can see my mouse, but we are definitely on the gray slope for the time being, and hopefully we will be able to change this tendency and going back to at least to the yellow, and why not also to the green tendency, where actually population can again thrive and be living harmoniously with us all. But that's not what you're observing right now, unfortunately, and it's not just sad for the species themselves, but there is also the problem that we rely a lot on the species for a number of things that are important for our everyday life. So there is a lot of these species that we use daily for manufacturing our food, for manufacturing our medicines, and losing this very rich biodiversity will have very important consequences also on our lifestyle in terms of lack of raw materials for production, or the purification of air, the purification of water, waste detoxification, and so on and so forth. So actually the biodiversity collapse, it's a really major crisis, and we are not playing now which is the biggest crisis like in the figure on the right, but the important point here is to just keep in mind that this is serious business. It's not just one little problem, it's ahead of us. It's probably one of the biggest problem ahead of us for the next years to come. Okay, but you could think, okay, how can AI help in all this? In the end, AI seems to have little to do with the biodiversity crisis, and more in detail to today's topic, to wildlife conservation. But actually, we can help a lot. And also, the first and foremost, by helping conservation actors who work every day in the field to protect animal or plant populations. Because people out in the reserves, and you have two examples here on the right, of some colleagues that we work together at Olpejeta or at Kuzikus in Kenya and Namibia, respectively. Rangers are out there and record and control populations. They fight poaching and poachers that are there to basically kill animals. I don't know, take their horns, if you think about the rhinos. And all this work, which is a gigantic work, imagine just the size of the natural reserves and the number of individuals to protect, is mostly done by hand. So rangers must rely on data samples that are very, very small. And even when data are available, because of some kind of imaging, we will see that in a second, it becomes critically difficult to process all this data and to be up to date with the processing so that decision makers have information that is actually up to date. So you see, hey, I can help in these two ways. So it will be collecting data and staying on par with the data, with the processing. And these are the two things that I want to discuss with you in this seminar. So how we collect smartly, and then how we process smartly. And this will be the two chapters of this presentation. So let's start with the first, which is the better data collection. And I wanted to show you here this figure from our latest paper, where basically make a kind of an overview of the different sensors that we can use to monitor and protect wildlife. And you see that there is a very wide diversity of sensor data that you can use, going from the satellite here on the top left, all the way down to the mobile phone when you think about citizen science and taking pictures of animals and plants during your recreational activities. So there is a wide range of these, and today we'll focus on two of them, one being drones, that you can see here in light blue, and then the community science, that is something that we will use to give values to this drone data. And to show you this, how we can use drones for conservation, I want to make a very practical example, which is the first project we had back in 2014, and that has been running ever since, every year. It's a project that we have together to a wonderful game reserve in Namibia here, which is called Kuzikus. And at Kuzikus, they contacted us in 2014 to see the potential of some kind of automatic animals population mapping. So first counting of the individual, and then if it was possible to extend that to population. And back in the day, we were not very knowledgeable about this, so we were maybe a little bit full of ourselves, and we thought, yeah, no problem, we just send a student with a drone. So we bought a drone, send them to Namibia, and then piece of cake. That's a very easy thing to do. Now, this might sound very simple, but then we had one lucky student who could fly to Namibia and spend 2 weeks there and fly the reserve in all different directions. And we ended up basically with something like this. Now we have the Kuzikus reserve that you can see here in all its beauty, the animal we want to sense. We then went there with a camera that must be as simple as possible, because we want a hardware that can be, maintained and implemented by local people. So we don't want to have a $500,000 camera put on a drone, which is also a consumer drone, very simple, not too expensive, and then basically fly it around to collect this data. So the student went there, collected the data, came back, and then we started to think, okay, the first thing we need to do is to create some annotation process where we can actually see where the animals are. And we were confronted with images like that. Okay, this is one of the images we have in the 2014 data set. And then, we started thinking about it and how to create this recognition data set that we will then use for machine learning for training the AI. And then to train a good AI, you need labels, so you need annotated data, and we started annotating those images. So now you have been looking at this image for a while, and usually I play a game with that. I ask the public to tell me how many animals are in the image. Unfortunately, we cannot play that because we are not in the same system. I'm on Zoom and you're on the neural network. But I can show you something that you have for sure seen. So these 5 animals are extremely easy to see. They are in the middle of the image. I center the image accordingly just to make it simple. But the question number 1 is, have you seen this 3 animal here? And maybe, you know, I've been talking for some time, so for sure you have seen something, but I'm pretty sure you haven't seen those animals. Or maybe you have, because, you know, the task of you're extremely good at the Where is Waldo game, which is very good. But you see, there are 17 animals in this image, and honestly, 9 out of the 17 are very difficult to find. So this was one of the challenges that we just learned by this first terrestrial campaign, is that the animals, when you fly a drone at 100 meters altitude, which you need to do in order not to scare the animals, they are very small. So on average, at that resolution, which is 8 centimeters, well, it's 30 by 18 pixels for an animal. They are scarce, so many images simply do not have any animals in there. So you spend a lot of time just looking at the savannah without having any image. And the animals are heterogeneous. So, you know, a zebra and a giraffe do not look exactly the same, an ostrich even more different. But not only the animals are very different between each other, but the landscape is very tricky. So sometimes you have elements of the landscape that look exactly like animals, like tree trunks that have fallen, they have a projected shadow, they are whitish, and they also look like animals. And then the background itself, as you can see here, it's very diverse. So now you're looking at 8 images that contain animals, but they are all from the same data collection campaign. So you see, we have to cope with 2 problems that are very interrelated: the diversity of animals on one hand, and the diversity of background, which occupies 98+% of the data that you have. So let's say we learned our lesson thanks to that first campaign that was called back in the day SAFMAP project, Kalahari Mapping Project, and we then became rightfully humble and say like, oh, that's very difficult, and a ranger alone will take days to spot all these animals in the pictures. But so if we want to make a system that is usable for the ranger and the people who are actually doing conservation, how can we accelerate this annotation process to have the annotation done in a range very useful time? And we also want to be sure that these annotations are of good quality. And because, of course, we could not do it by hand every single time we were going, or every single time someone in a natural reserve was flying a drone. So the first thing we decided to do was to try out a crowdsourcing campaign. So we teamed up with a number of colleagues, and most importantly, the AIDR team in Qatar, and we developed an app basically where anybody from their smartphone or a tablet could look at some images from this Kudzikos dataset and basically annotate where the animals are. So you see there was just 2 buttons. It's very simple, nothing here. Or if you click green, you can then draw on the pictures and we record the annotations that you do. And this proved to be very successful because people were very excited to help for nature conservation. I know crowdsourcing is not always that successful, but probably the topic was really feel good and people wanted to help. So we had our 26,000 images in the acquisition of 2014 with only 1,000 animals. So you imagine how many empty images were in there. And by crowdsourcing, in 2 days, we had every single image looked at by 5 digital volunteers. So this was a very big success because on one hand, we could go through the whole data collection that we had done in Namibia. And at the same time, we finally had the data we needed to start training AI models. So, of course, it was not just so simple. The application on the back had some AI to show to the people the images that were more likely to contain animals. And we wanted to also showing more images where there were inconsistencies between annotators. So there was a fair amount of machine learning behind this app. But basically, we ended up with something that looked like this, where you have this herd of animals here that were detected by the 5 annotators. So every polygon you see here is one person annotating. And then there was, for example, one person that annotated incorrectly this one, but since it was only one of the 5 annotators annotating this part here, this could be easily removed from the actual final annotations, because it has not been agreed by the others. So we could use a kind of a majority voting to be sure that what was observed was an animal. And of course, I mean, this is what we did in-house in 2014-15, but the field has moved at an incredible speed in the last years, and there are other platforms that now are doing things that are frankly incredible. So, for example, Wildbook, it's something that I really like, because the Wildbook system actually mines social networks like YouTube for videos of whale sharks and try to identify them and interact with the video poster to know the identity of the animals. There is eBird, where you can basically annotate where you saw some types of birds. And then iNaturalist, that maybe you have heard of, which is also based on mobile phone tagging. So you tag the animals or the flowers that you see during your recreational activities. And this goes into an AI model that will tell you which species you are looking at, and also puts it on the map. And the map is getting better and better. As you can see here, this is a naturalist. And we have millions of observation of hundreds of thousands of species. And this is actually fantastic, because it becomes open source, open data that everybody can use to then study and model species distribution, which is something that there is a whole community that is actually raising to answer this call to help in the fight against the biodiversity decline. And remember, it is not just data collection. There is a ton of AI behind this data collection. For example, there is a lot of active learning. So how to show to people the most interesting images when they label. So are these images where the model is struggling selecting which one is the right species? Are these images where different annotators disagree? There are different papers that you can see. I just put them here on the slide. Or also learning from crowds. It's something that it's very interesting and passionate, where basically you try to leverage single annotator strengths and make them work on some species and not another by learning about their behavior, or also to detect frauds or people that are trying to disrupt the process. All right, so this was for the data collection. Now let's assume that we have some data that we like. Let me just have a sip. And at this point, with these images that we have acquired and the annotation that we've had from crowdsourcing, we are ready to learn some actual machine learning models. So as you can see here in the image on the left, you can do different things when you have this type of data. You can identify single animals, like seen here in green. You can discriminate the species, so the different colors of the boxes below the animals. You can do pose estimation and skeletonize to see where the different parts of the body. You can 3D reconstruct the environment. There is a lot of things that we can do where we have images from above or from camera traps and some knowledge from AI. But coming back to our example of before, basically the thing that we want to do is from these images that we have acquired with the drone, we want to basically detect and bounding box the different animals. And with a little bit of luck, also knowing which species they belong to. For those who are not familiar on how this works with machine learning, I have here a very short video about how it works. I just played, and it's a couple of minutes, and it's fun. And thanks to Benjamin Kellenberger, who helped me out with it. So when you learn a machine learning model, basically what you do is that you have an algorithm that is presented with pictures and with its own internal parameters tries to answer. Of course, at the beginning, it makes mistakes, but every time it makes mistakes, you will change its internal parameters, as you can see here, and then keep going and repeating the action for many, many, many cycles. And as you can see, the answer is very often wrong at the beginning, but sometimes it gets it right. And when it gets it right, you don't change the internal parameters, but you do it every time the answer is wrong. And after some hours of learning, the model will have learned which visual elements of the original image correspond to which class. In this case, some very cute animals or sometimes a car. And after some hours of learning, we are basically ready to go to predict in new images never seen before with the machine learning algorithm. So we want to apply this same idea to our problem of identify animal presence in drone images. So here on the left, you see the drone image. So it's 500 by 500 pixels. There we have chunked the original image in a small square, and we have 3 bands, RGB. Then we have a model that we run the image through, and at the very end, we want to have a map, which is much coarser than the original image. You can see it's 32 by 32. And at every pixel in this final response map, we want to know if an animal is absent, so in this case, probability is 0 in black, or if an animal is present, probability of 1 in white. Okay, so this is a model that involves some kind, it's a neural network, it's a deep learning algorithm, and it involves some processing stage that we will see in a second. But basically, it's something that can be trained if we have this annotation that we were talking before. So if we have a map like this that tells us where the animals truly are, we can predict with the model, see if the prediction is correct. If it's incorrect, we can change the model a little bit and then have a better model until the model will get the position right. So are we ready when we have something like that? Unfortunately, no. So remember that we have more or less 1,000 animals in our data set, and we have 654 big images. And when they are chunked in the small patches, it's roughly 26,000 images, as I said at the beginning. So this means that we have roughly 700,000 pixels corresponding to animals, and this incredibly big number, billions at least, of pixels that pertain to the background, which means that it's very, very difficult to find some feedback signal corresponding to the animals because they are so rare. So training a model in this naive brute force way is not possible. But in this work here of 2018, we tried different strategies to train a neural network in a way that makes sense and that it allows the network to recognize what animals are and not just being confused by the enormity of background pixels. So, for example, the first thing that is much used in deep learning is to do some pre-training from natural images. So we have this gigantic data set like ImageNet, and we have models that are already trained on ImageNet so that they can recognize cats, dogs, airplanes, like in the little video I showed you before. And we can take those models as a starting point because those models are good at image recognition, which is what you're trying to do. The only thing they do not know is how to recognize animals in savanna from a top-down perspective. So with the limited data that we have, we are able to make the model a little bit smarter to recognize this type of conditions while leveraging all the very low-level visual primitive learning that was done on ImageNet. A second one I want to talk about is the curriculum learning, where basically we start the learning with a problem that is simplified. So we start showing to the model only images that have at least one animal in, so that there is always something to be found. There is never a situation where the model should not predict anything. And when the model has understood what an animal looks like and the type of different backgrounds it can encounter, then we just open to the ensemble of the dataset, where very often there is no animal to be found, so the model can tune on the background only. But okay, long story short, with these 5 different strategies, when used together, we arrived to a detection of the animals in the QCCODES dataset that was close to 90%. So you can see here the recalls. It means that we find 90% of the animals that were in the original data, which is great. And also, we have a precision here that is much higher than the former state of the art. You can tell me, okay, you go from a 2-3% to a 20%, but 20% is still very bad. And fair enough. I mean, it's not perfect, but if you look at it in another way, we are decreasing the number of false positives while predicting from 20,600 to less than 1,000. So it means that to predict basically 90% of our animals, we make more or less 1,000 mistakes, which is something that a ranger can review in a decent time, while reviewing 20,000 false positive has two main problems, which I tell you in a second. Now, the good news is that we keep working on this, and now it's more or less where we are. So you can see here on the orange line. So we are still in between 80 and 90% of finding all the animals that there are, but this time we are maybe 70% precision, which means that we have a very small number of false positives. So, it means that you are much more precise. So the blue square here are the prediction of the neural network, the green are the true animal locations, and the red is what this other former baseline is doing. So we are doing much less errors, which is the first benefit, that we are detecting better the animals. But the second one is that in order to detect our 90% of animals, we need to screen roughly 300 images, right? While the former state-of-the-art to detect 90% of the animals had to screen 1,500 images, which is almost the entirety of the data set. This means that in the former models, we were indeed still detecting a lot of animals, but at the price of the ranger having to control every single image of the dataset. So basically, there was no gain in effort because the ranger had to relook at every single image one by one and to see which detection were wrong and which ones were correct. I mean, at that price, you can just do it by hand. While with this new deep learning based model where we use all these different strategies to learn, basically the ranger has to screen only 1/5 of the dataset, which is a significant speed up in time. I think this is a good take-home message for this type of methodologies that basically makes detection much more precise, and it makes rangers save a lot of time. And this is getting a lot of traction, and it is now being used more and more by actual departments of fish and game, like in Idaho, where a colleague, Sarah Beery, is using their mega detector. Maybe you have heard of it, which is also a model that detects animals, empty images, humans, and vehicle on camera trap images. So not drone, but cameras glued to trees. I mean, I don't know if glued is the right word, but so using the mega detector, you can have these camera trap images, see if there is an animal, and if there is an animal, we can then map them, and this actually makes that less than 15% of all the images acquired require human review, while before they had to review the whole set of images acquiring, which was also why they were very, very much behind the actual image acquisition. Or wildlife protection solution is active in several countries to detect a vehicle that is a kind of a proxy to see if there are threats and poachers in different parts of the world. So these models are now entering the realm of practitioner, and I think it's fantastic. But then, of course, there is much more than that. There is a number of other applications that you can imagine while using AI for wildlife conservation. So you can see here on the left, for example, tracking of animals. So you can see this fox that is wandering around. This is the work of a colleague, Benjamin Risse. Or on the right side, the works of Silvia Zuffi, where they do 3D reconstruction of animals from videos of animals in the wild, which then allows you to basically move the animal around. The animal is textured, and you can have all kinds of digital twins, study behavior, health of the animals, and so on and so forth. Okay, so now we have collected the data. We have some wonderful AI methodologies to detect. Now, how can we close the loop and give back to the rangers that need this technology for their protection action? Well, basically, the thing that we are missing is something to make this model here interactive. I'm sure that many of you have been looking at this figure and have thought, but Devis, what are you doing? Some images here are missing. And so either you thought it was very lazy, which I hope not, or you maybe imagined that there was something more. And in this part, I want to talk on how we can now develop strategy to detect animals that are missing. So as you can see them here in green, so animals that were not detected by the original algorithm, or prediction that were made and they were wrong, like this tree here or that tree here. And this joint work with former colleagues, you have seen Ecole and Diego Marcos, who were among others, and Benjamin Kellenberger as well, working on this type of problem. So we started with the idea of what ecologists need. Okay, the ecologists need to give value to the imaging campaign. So they take a lot of images, and very often it's very difficult to keep up with the number of images taken. And the machine learning expertise is not forcibly always extremely up to date. So they want to do it with some environment that is easy to use. Rangers, they need to monitor their animal population often because they need to maybe change their management strategies in the research, and they don't want to make a labeling campaign on the internet like the one we did every single time. Mostly because they don't want their images to end up on the web, because come on, if I was a poacher, I will just participate to these games and then I will know exactly where the animals are all the time. So maybe not exactly, but if you know the region, seeing the images tells you a lot already. So this is what we started to work when we with a collaboration we had with Microsoft. So Benjamin Kellenberger went to Microsoft as an intern, and we basically started developing this software suite that we call AID. It's the AI interface for ecology, and it's basically constructed like this. We have concurrent access by whoever has picture that they would like to use to count animals, camera traps, drones, satellites, you name it. And these pictures can be brought into this environment. It's very easy to use, so you can click on the animals, you can draw bounding boxes, whatever you want. And then you have access to a number of deep learning models that are there pre-implemented for you. And you can train on your data these models directly on the cloud in Microsoft Azure. And not only you can train this model and get your prediction, but you can get your prediction back to the user in order to have verification, extra labels in areas where the model is unsure, and so on and so forth. So it's really a kind of a synergy between the user, the ecologist who acquires the data, and the machine learning part of things where the model is optimized. So AID is able to ingest very different types of data. It can be camera traps, so you just want to have the class for the whole image, like giraffe here. Maybe you want to count animals, so you want to point click. You maybe want to do bounding boxes, or you have satellite data and you want to do land cover mapping. You can even draw your ground truth and use semantic segmentation model. So there are several models, and they get more and more in the AID models. And the thing that we are really the most happy about is that it is 100% open source. So you want to use AID, you can. You just flash this QR code, you go to this website, you download it. If you have trouble, you contact us and we try to help you out. But this is the good thing, is that AID is for the community and it can be used by anyone openly. And it is starting to be used here and there. For example, you see here one application that we had the pleasure to support. It was in Western Africa, where our ecology colleagues from Quest wanted to count migratory birds into different classes or different species of birds. So we wanted to know how many and of which species and how they organized in space. And thanks to AID, we could run the pipeline of detection and counting in approximately 4.5 hours, including the model training, while usually that would have taken them roughly 3 weeks manually. So a significant speed up and a very interesting collaboration between ecologists and machine learning specialists. Okay, well, time flies, and it's more or less already time to conclude. Let's start by saying that I hope that you have appreciated this very short overview of the things that we can do to support ecology with machine learning and computer vision. But if you remember from my title, the title was machine learning supporting ecology, supporting machine learning. So the question that remains, and I just would like to briefly discuss, is whether machine learning actually needs conservation in the sense that are these problems that are interesting and novel for machine learning as well, and what are these like very exciting machine learning pathways that we still need to explore to get there. So the first thing that I always find a bit striking is that we predict all the species as if we knew nothing about biology, while we always know, for example, taxonomies of species, and it's we know which two species are from the same genus or this type of relations, and this can be integrated in machine learning models pretty easily. For example, like in this paper here by colleagues from ETH and University of Zurich, where they used actually taxonomies between plant species in order to have a better recognition of the plants by the deep learning model. Other information that are very seldomly used are information about position and time. While sounds pretty obvious that not all species live at every corner of the world, so some species like to live in some specific ecosystem, so we have species distribution models that do that very well. But actually, in our machine learning models, we kind of tend to want to learn everything from the images, while the location where the image was taken, as well as the time, will tell us a lot about the patterns that we are expected to observe. And there is this wonderful paper by Macado and colleagues, where they actually encode this information together with the information coming from the image to have a better species distribution modeling. And as you can see in the image here below, I mean, the patterns differ significantly, both in space and time. So it's something that makes total sense. Finally, there is also knowledge from behavioral ecology or ecology at large about the interaction that the species like to have. And this means that some species like to co-occur, some species predate each other. And this is also information that is there and craving to be incorporated in ecological pipelines based on machine learning. All this to tell you that there is a lot to be done, and that it's really, really important that this field stays strong, and that there is a lot of research being done. And we try to do our part, so we are launching very, very soon a new project called Wild Drone. So it's wilddrone.eu. Here you have the URL if you want to know more. And it's a Marie Curie doctoral network, an action that will involve 13 PhD students. So we are recruiting right now. So if you know of very talented students who are finishing their master right now and they want to know in digital ecology, please send them our way. We will have this 13 PhD working at the interface of conservation and ecology, computer vision, and drone operations, so robotics. And we will really make the links between these three words and really make them work together through a lot of fieldwork in the African continent, trainings of all these cohort of PhDs in order to train the person that hopefully will help us fighting the biodiversity crisis of tomorrow. And saying that, a very last slide of thank you for all, I mean, not all, but some of the people who have been with me in this now almost 10 years journey. You see them at the top. And at the bottom, again, a little wink for the Wild Drone project. Please visit the website. Let us know what you think. And yeah, that's it. Thank you for your attention. And if you have some questions, here I am. And I'm very happy to try to address them somehow. Thank you.
Thank you, Devis. A fantastic presentation. I'm in contact also with people sending me messages on WhatsApp and email saying, oh, wonderful presentation, so interesting. So thank you.
Oh,
I see a lot
you.
of excitement around this presentation. Also, everything was very clear. So thank you so much for the presentation, staying in time, being so clear. But there are some questions for you. So
do you want
I would,
to stop sharing the screen, or I keep it on?
oh, as you want, no, you can stop the sharing in such a way that we can see you better, because I don't think that
Okay,
is needed.
let's do it. Here
Yes.
we go.
Okay, fantastic. So we have some questions, first of all, and then I have also some curiosity. The first question is from Dulce Blanca Punzalan. And what are the top deep learning use cases? Species identification, assessment of animal health, feeding patterns, and migration.
That's a good question. I will say that the field is very young, like the not the migrations but the deep learning approach to the animal ecology. It's something that is pretty recent, I will say. So I will say that most approaches are now still in the detection phase. So we're trying to detect and count. And now people are getting more and more interested in population mapping, migration, detection of threats, like how to detect sentinel individuals that will tell us where the poachers are. But there is, I mean, the community is it's really starting to grow a lot. By the way, we have a Slack channel, AI for Conservation, where we discuss all the things. It's 1,500 people now. So if you want to join, just send me an email, and I'll be very happy to have you in and discuss with us. But the thing that you said, there is a lot of acoustics, so try to recognize animals by their sound, and yeah, it's really taking off. And but I think we are just starting to learn what are the real problems in ecology, and this is why we need ecologists in the loop.
Thank you, thank you. Then the second question is if does IDE also work for vegetation, for instance, counting trees?
Counting trees is a problem that is probably is older than animal detection with deep learning, at least for the remote sensing person than I am. Detecting and counting trees is something that has been tried maybe since 20 years with different degrees of success. But there are models around that work decently well, especially in areas where you can see that it crowns very well, or where you have a very precise elevation model, where you can use all kinds of strategies to isolate single trees.
The advantage is that trees are not moving.
This is true. This is true.
Animals, they move. That is
I have a student working on the tree line here in the Alps, and if I showed you the time series, I could show you the trees actually do move. I mean, it's not the same trees.
Now, it could be also different status of trees, like different status of health of trees.
Absolutely,
or something like that. So yeah, this is also, I believe that in the future we can consider this IDE also for these cases.
Yes.
And I have a general comment to you, because with respect to the collection of data, have you considered the gaming? So use games to collect the data? I mean, yes, you said we don't want or they don't want to share the images because it's a problem for the poachers, but if those images are inserted in some realistic games, could be that this can help, as a matter of fact.
Okay, so if I understand well the question, you're suggesting to use game engines actually to generate.
Yeah. Oh, it's not my idea. I have to say that the idea is from Alessandro Annoni. And speaking last day about digital Earth, at a certain point he said that it's very important to consider the possibility, because now we have realistic images, as a matter of fact, and the games engine are very, very powerful. And so it could be that we can use something that is true. We don't need to insert in the right place, probably, in such a way not to create problems to the animal, but we can use true images, asking, for instance, of detecting something there and save these pieces of information because they can be reused.
Absolutely.
So people can be aware or not aware about what they are doing, as a matter of fact. So this is one possibility because there are many people doing this kind of games. I'm not a gamer, so I don't know, but I know that there are many students of mine spending all the day gaming. So
Oh, I'm guilty as well. No, but it is something that in computer vision has been explored a lot, for example, for autonomous driving. So using gaming engines to have photorealistic type of environment where you can basically make anything happen. And there are also suite for that for drone flights. And in the past, we were working with our colleagues at Microsoft in trying to have a Savannah simulator. So we had one student working on that. And I mean, as a generator of training data is good because the moment the animal is simulated, it becomes a training point and you know exactly where the animal is because you are controlling the simulation. So you can plan a virtual flight in your digital environment and acquire images from different angles and have a ton of training examples. The problem is the photorealism. So the photorealism is still something to be achieved in African savanna environments. It's less developed as in urban environment for autonomous driving because those simulations are really bluffing. While the savanna we had was looking very nice, but we had no control about light and the time of the day and this type of thing. So it was a bit difficult to have the data we needed for the model not to be fooled too easily, because if the feel of the scene is not realistic enough, the model understands very quickly that it's fake data and doesn't learn from it. And this is what happened back in the day.
Yeah. Oh, another question for you. You spoke about ImageNet. So I don't know if you wanted to add some pieces of information about it, because I'm pretty sure that not all the people attending this webinar, they are familiar with the ImageNet.
Okay, ImageNet is a big data set that was collected by our American colleagues in Princeton and Stanford, if I remember well, Fei Li and Olga Rusakowski. And it's 14 million images, if I remember well, classified into 1,000 classes. And these 1,000 classes are all kinds of things. So it can be objects, it can be images of a cup. Can you see my cup? Yes. Images of airplanes, trains, cats, dogs. And this very big data set was collected, labeled by people using mechanical Turks, these type of things. And it was then given openly for computer vision research. And it's basically the data set that allowed all the first big models for deep learning to be trained, like AlexNet and the like. And so maybe in a way, having this enormous data set to train model is what enabled big neural networks to happen. And since these models are learned on this very big data set, they share this low level color gradients and little details between the images taken in that data set and our images from the drone. We can transfer information from one to the other.
Okay, so reusing this ImageNet, we can say is like instead of taking a kid of 2 years and start teaching him or her of doing something, to take a kid of 4 years who already knows something and starting from there and teaching something more detailed, like one specific species instead of
Exactly. You need to imagine these networks are millions or tens of millions, hundreds of millions of parameters to be learned. You can start by random numbers, so the 2 years old.
Yes.
Or you can start by numbers that have been proven to be able to recognize cats and dogs. So you know that borders are sharp, they're usually oriented like this or like this or like this. So these very low level features are learned. The thing you need to learn now to the kid is what an animal looks like, which is a composition of all these very small things.
Okay. And then there is another question from, so I don't get, but there is another question. Are other geospatial data sets like sensors used in this work? Maybe it was mentioned, but cannot recall.
In the works I presented here, we mostly used drone images, color images, so because we were using these very cheap cameras for the detection of animals. But in principle, I mean, any kind of image data can be used as long as we can make it fly, or put it on a camera, fix it on a tree or on something that is static and can image a scene. Now, it's definitely possible to also work with 3D data. For example, LiDAR point clouds. The moment we can create images from the point cloud through all kind of ray tracing or things like that. Thermal images could be good, but not in the case of African savanna, because the temperature is so high that you don't collect the thermal signature of the animals. Yeah, I mean, the world has no limits. No, the moment we can use this data, microphones and sound. I was talking about.
The more, the better.
The more, the better. The difficulty is to make all this data occur and learn jointly from all of them. This is very difficult.
Yeah. Oh, the question of before was of Andrea Manara, and now we have a question from Mansi. Wonderful presentation, Devis. What computer vision models did you use? And looks like you have used some transfer learning.
So the computer vision model is, at least in the first work, was a very plain ResNet, learned from Worm started on ImageNet, and then we had a few extra convolutional layers that we learned on our own data. So it's really, there is some kind of transfer learning. I mean, I don't like to call using pre-trained model transfer learning, but in a way maybe it is. So we can. In the work about the migratory birds, we were using some priors about density of birds to recognize the species. So we were using a marker random field on top of the neural network, because we knew that the different species tended to aggregate in different ways. So a certain type of bird liked to be closer, another liked to be more spaced. And thanks to these priors, we could rule out wrong predictions of the single animals, like the class memberships. There were some work where we use weakly supervised learning, always with the same backbone, but instead of providing precise bounding boxes, we were only giving overall counts or presence absence at the image level. So if at an image there are animals, you say yes, and this is the only supervision signal you get. But you can still learn localization from that supervision signal, which is something we didn't expect, but it was very fun. I don't know, these are examples, and yeah.
Okay, thank you. We have the last question now, Guillaume Emmert. Very interesting presentation, Devis. I agree. Could you elaborate a bit on the methodology for data capturing and animal counting? Did you limit animal tracking data to specific regions or areas? How did you assemble the data?
So the data I showed in this presentation are our campaign of 2014. So at that time, we basically flew, how much was it? We flew for 1 week, and we flew roughly 15% of the reserve, which is, I mean, it's a big reserve. So it took us a full week. And we were basically planning the flight mode of the EB so that to do patterns that were kind of squared, and we would not have to go too far to collect the drone. So in principle, if the drone comes back pretty close, it's easy to go and collect it. And we basically made our counts based on the image covered in that collection campaign, knowing that sometimes we have some double counting because animals move, as Maria correctly said. But this is something we can always, always need to take into account. And also, in a way, yeah, there are double countings. Okay, but what was happening before was renting an helicopter, flying 1 hour, looking out of the window, coming up with a number, multiplying by X, which is the size of the reserve. And also the risks involved were huge because I don't know if you know, but the first reason for casualties of biologists in the field is actually discounting campaigns on helicopters. So after for safety, it's good not to do it.
Okay, so thank you so much again, Davis. Thank you for the presentation. And for people who arrived late, I want to tell you that the presentation will be available on YouTube in such a way that you can attend later. And if people have other questions, I believe that they can contact you.
Sure.
Yes, and then if you want to say for the last time that you are searching for people who are interested in working in this topic, I leave you the word, and then the very last word will be for Andrea.
Okay,
But now,
good.
if you want to advertise again,
Let me have my best shot. Okay, if you're interested by fighting the biodiversity loss, if you're interested by wildlife conservation, and you love ecology, computer vision, machine learning, or robotics, and most importantly, the interaction between the three of them, we have 13 positions all across Europe for PhD. So please go to wilddrone.eu, have a look, and apply.
okay. Thank you so much, Davis. Thank you.
Thank you very much for having me.
Yeah. And then we leave the word to Andrea now.
Thank you
Bye.
very much, Devis and Maria. It was really a very nice session, and I thank also the audience for really engaged participation. Really, I found this session very interesting, very didactical, and we learned how combination of different kind of geospatial data, machine learning can really assist in ecology and in fighting the biodiversity loss. Before ending this session, let me remind you that in mid-December we will hold the final event for the GeoAI competition. We had three problems. One related to crop mapping from FAO in cooperation with the UN Open GIS initiative. We had a problem on school mapping with satellite data from UNICEF, and on location mention recognition with the social media data from University of Qatar. Again, the GeoAI competition is a competition in which anyone with a knowledge of machine learning can participate to solve problems in the geospatial domain and also win prizes. We are putting now the link in the neural network. As the registration is open until the end of November, and if you are a really hard worker, you'll be able still to participate and maybe win some awards. I have to say the topic which was under discussion this afternoon was really very interesting, and so I will definitely see with Devis if he's interested in cooperating with ITU for next year competition. I thank all of you for your participation, and with this, let me give back the floor to Anna.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
you.